Hi everyone. So I'm Jeroen from I did one of the two Google Summer of Code projects this summer on integrating the new constraint planning capabilities into the existing MoveIt interface. So first, why is planning with path constraints useful? I think it's maybe clear to almost everyone, but there are some example problems here that we would like to solve. On the left is a typical problem in almost every paper is if you want to move a glass of water and you have to keep it upright, there are some orientation constraints on the end effector, on the gripper in this case. And then we have robot welding, for example, of in the case of this specific planning algorithm I will talk about, there is also the Robonow 2, which has to do these complicated motions inside a tight container and then has to grab these rails at the side. And this is also a path constraints on an end effector, but on a system with a lot more degrees of freedom. And so to solve this type of problems, there is already an existing planner in MoveIt. Deep inside the interface of MoveIt, it's called a post-modal state space or post-modal, but there are some known issues with it. So you can see in the animation that there are these jumps in joint space that often occur if you try to plan with path constraints, and especially if there is an obstacle, then you get these results. And so these paths cannot be executed on a robot. So before I explain the new approach, I will try to quickly, very simplistically explain the background to be able to explain it, but maybe most people know this, but here is a simple 2D robot with, and the green box are constraints on the end effector, so the last point of the robot has to stay within this box. And so the typical approach to solve this is to look at a joint space. So if we plot two angles, we get representation of the joint space of the robot, and then the green box or the constraint will not be a box in joint space but some weird shape. And then the current planners in MoveIt can solve this problem in two ways. So rejection sampling is shown here, where you generate random samples in joint space, throw away all the red dots, so the samples that do not satisfy the constraints, and then try to plan for a path here. So it could be that you have to move from this point to this point, and then this is your solution. The other approach is in MoveIt is shown on the right, and this is a planner that plans in task space. So instead of planning here, it directly looks for a path in this green box in task space and then tries to come up with a joint space solution. But so it's possible that the corresponding joint space solution switches between robot configurations or something, and then you have these jumps that occur, and it's the long-standing issue. And so there is another planner in OMPL available for a couple of years already, and it's another approach to planning with constraints where you create random samples and then instead of throwing away the ones that are invalid, you project them onto the constraints, and this way you can generate many valid samples but still plan in joint space. And this also works, for example, if you have constraints that are a line in joint space or small or zero volume. If you randomly generate points, you will never find configurations that satisfy this constraint. And so with a new planner, this is possible. And it was also possible, of course, with the task space planners. So the difference now is this is the current implementation in MoveIt, the post model, and then for problems like this, you can see again these joint space jumps. And this is also a problem where you want to stay with the end effector, a point on the robot here in this gray plane. And so it's difficult to solve this problem, or impossible even with the rejection sampling approach here. So you have to use the post model state space, or from now on, you can also use the new planner, which for these types of problems generate these paths without this problem. So this is the solution, and then how it's implemented. Before I added the new code, I did a lot of cleaning in the current OMPL interface. It's a complex piece of code, so it took me a while to understand all the pieces, and while learning it, I cleaned some things up. I removed some a couple of lines of code that were never used, and also fixed a small but interesting bug in the existing interface. And then while writing the new code, I also wrote a lot of tests, and some of these tests are also very useful for the current interface. So this is not new code, but these are tests for the current interface that really help in adding new things, and also kind of serve as documentation for the internals of the interface. And then the actual exciting part is the main pull request, where the constraints are added. It's quite a large pull request, and it comes together with a new tutorial. So I created two simple examples using the Python interface to show how you have to set up and use this new planner. So these are two of the examples of the tutorials, so that focus on cases that are interesting for this planner. So moving in a plane with the end effector or along a line. But there were some unexpected problems that I quickly want to go over. So the first one is that this projection-based sampling approach turns out to generate a lot of samples that are invalid due to the fact that they are projected outside the joint limits. And so we could solve this problem in two ways. Just we could throw away all the invalid samples. We had still 20 to 50% of samples were valid. Or we could try to model the joint limits also as constraints and add them to the planner and add them to the projection step. But this turns out to be very slow compared to just adding another layer of rejecting invalid samples. So now we have OMPL planner that projects the samples, and then in MoveIt we do the standard check of the constraints again. And then if you go through the final pull request, there is the elephant in the room that the orientation constraints are not there yet. We discussed them extensively during the project, but it turns out that in MoveIt, the orientation constraint tolerance is specified as Euler angles. And for the projection approach used in the new planner, Euler angles doesn't work that well. So you can't really project on Euler angles, and it would be very useful if you could change parameterization to angle axis, which is already used in other planners such as Trajupt or quaternions. So I created an issue to discuss this, how we could add another parameterization to MoveIt. So this is a quick example of how it would look. For now, you can specify 3 values to specify orientation tolerance. And so as Felix proposed, for example, that we add another 3 values for another parameterization, or we could introduce different orientation parameterization types in the message format. So this is ongoing. When is this planner interesting for problems? So it's especially for this so-called zero volume task space constraints, planes, lines. Also, a glass upright can be seen as such a problem. And I also experienced that it's mostly the case if there are obstacles, then the post-model state space has these joint space jumps. But if there are no obstacles, it works fine. So you can just use that if you want. And then if you have constraints that are, for example, a large box or a sphere on a robot link, then the rejection sampling also works very well. So this enforced joint space model was introduced, I think, a year ago maybe, and this you can enforce the planner to use rejection sampling and avoid the problems with the post-model state space. But the interesting part with the new planner also is that it's extendable. So the most of the code around it is just to interface the OMPL constraint planner with MoveIt. And once this is up and running, you can add new types of constraints any way you like. So just to show that it's not really magic, I added 2 implementations of box constraints and orientation constraints. And so you can implement any kind of error function as long as you can express the distance to your constraint, and this planner can try to solve your problem. And here you see the angle axis constraint. So it's a rotation axis times the angle, and that's a 3-element vector that is used as the error. So again, I would like to invite everyone who is interested to look at a pull request and discuss and give some feedback, and also maybe try out a tutorial. And then to finish it off, I would like to really thank my mentors, Felix, Mark, and Omid for helping me and supporting me and reviewing a lot of the pull requests. And then also the MoveIt maintainers, of course, and especially Michael, Mark, and Robert, and Tyler also for reviewing and quickly merging many of the cleanup pull requests, and everyone in general who provided feedback. Thank you. And then there is time left for a Q&A, I guess. These are some other examples. Thank you for listening.